The classroom is full, so it means it must be a Thursday. Welcome, everyone. Let's take a seat and let's get going. And we have a recording going on. Excellent. Excellent. So, the past 2 weeks, slowly, we are working ourselves to the more interesting parts of the lecture. I hope. It cannot get worse than this. People are happy. Okay. So, we covered what we said was combinational design. In the beginning, it didn't look like it will do much, but hopefully at the end of last lecture, I was able to convince you that the things that we learned were actually sufficient to design the heart of a computer. Now, we've done the heart of the computer. What else is left? Well, we have to stitch it somehow to the rest of the computer, so there are still things needed. Today's topic, if I can switch the slides, is we will move from combinational into sequential circuits. And the only difference we will make the argument is that sequential circuits somehow have memory. So the only thing we will have to learn is how does a digital circuit remember things? How does it not forget it? How does it keep it? Because combinational circuits were such that you provided a set of inputs, and the moment you had the inputs, you knew what the output was going to be. Now, sequential circuits can also remember things. And for this, we will see what is the basis of memory in digital circuits. How can we do that? And then we will move to a topic that shows us how to construct circuits that control things, have different actions, can remember where they were, so that you can go to the next stage, and then the next stage, and the next stage. We will call them finite state machines, and we will do that. Now, are we ready? Good? Awesome. So, as you said, outputs of combinational circuits depend only on current input values, which is technically very good. It makes them very reliable. It's easy to visualize them. You write a truth table, provide a couple of inputs, you have a couple of Boolean equations, you know what the outputs are. Easy, nice, and predictable. Also, sort of kind of boring, because all you end up doing is writing them in equations of sums of products, products of sum, something. Now, the outputs of sequential logic also depends on the current input. It's not like they don't like input. They like the inputs, but the prior input values as well. It has memory. It remembers the state it is in. It's kind of like this annoying friend you have and saying, yesterday you weren't nice to me, I'm not talking to you. It remembers what was yesterday. I mean, who does that? So, some definitions, first of all. In digital circuits, we will call state all the information about a circuit necessary to explain its future behavior. So this is a thing that it is memorizing. It may not be a single bit. It may not even be stored in one part. There might be different parts of the circuit that stores pieces of information. All of them together, we will call them a state. We will hear about latches and flip-flops. These are individual elements, one-bit elements that can store part of the state. So we will combine multiple of these to store the state in a circuit. And we will call circuits that are made out of a combinational logic, which we already know, and the state elements we will call synchronous sequential circuits. Now, once you say synchronous, you will also say, are there other ones? Yes, there are also asynchronous circuits, which are evil and taboo. No one will talk about them during this lecture. For those of you who are watching on video and are upset with me, asynchronous circuits are wonderful circuits. They have their uses, but at this level, we will not be discussing them. It's difficult, Okay, so once again, sequential circuits will mean combinational circuits, which we already know, plus state. This makes our lecture today very, very easy. We will just learn how to define the state, and then we go home. The only additional thing is to store the state. So we will have things we call flip-flops. There's a lot of Californian, terminology in digital circuits. Latches, and something we call registers, which is a collection of them. The way we will see how these things come together is that these registers, these state holding elements, will divide the operation into distinct steps. At every step, the following is going to happen. We have our state holding element, and there will be a signal telling all state holding elements memorize. At that point, state holding elements will look at their inputs, memorize what the input is, and store it and make available to the next state. Now, once these guys have memorized the input and copied it to the output, the combinational logic all of a sudden will get new inputs. And they say, oh my God, I have to do something. So they will be thinking about it, AND gates, OR gates, inverters, things changing around and additions happening, carries propagating. And this will take a while. And then at the end of it, there is another state holding element that is ready to memorize it. When will he memorize it? Well, we will determine this. We will look at it. We will look at how much operation is needed, how much time is needed for all these calculations to complete. And we will adjust what we call the clock period, the clock signal, so that there is enough time to calculate what will happen next. So in effect, we know the present state. We might have additional inputs, take the additional inputs, take the present state, try to figure out what the next state is going to be. We do calculations, 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 and at some point, even in the worst case, even if my calculation is very difficult, remember we were propagating carries back and forth, all of these things have happened, I gave them enough time, and now we will tell the state element, memorize it. When we talk about synchronous circuits, not asynchronous, synchronous circuits, this memorization period, this time where the state holding elements do the memorization trick is fixed. We already have defined, for example, we say we will use a 2 gigahertz clock. This means that a signal that changes from 1 to 0 2 billion times a second. Or, if you look at the time, it will change from 0 to 1, and then back to 0, then back to 1 in 500 picoseconds. If you think that's a short time, you are right. It's a very, very short time. And in this 500 picoseconds, hopefully our next state calculations will be done, and our register will be ready and capture it. We call it synchronous, or why we call it synchronous is because every state holding element in the entire circuit will do this memorization process at once. It is like a communist structure. Now, like everybody, 10,000 people, look left, memorize, I memorize it, here it is. At the same time, in like unison, like marching down the street. The opposite way is more like an anarchic way, like every little state holding element saying, okay, I'm done, how about you? Is it okay? And these things makes life difficult for the designer, that's us. So we will only concentrate on the sequential operations. How fast can we finish the operation? Well, this is our main problem, but it is not the sequential circuits that limit us. It is the combinational circuits in between these state holding elements that will keep us kind of busy. Now, you will hear a lot of these terms because I'm not so disciplined. I will mix them a number of times. I have to switch this off, I heard, just a second. Data path versus state machine. I will try to keep it here. Now, in a digital computing circuit, what is happening a lot is we have big data moving in. And this big data, data bits, 64 bits, not cloud kind of big data. And we manipulate them, we do operations on them, we add two numbers, we maybe multiply them, the result, we do some interesting operations. Maybe we make decisions whether or not I take the output of the multiplication or the addition. I might also have an adder subtractor, so I might have a mode that decides whether or not I'm subtracting. We forgot that for multiplication. Maybe we need another bit. In short, we have a flow of data moving from one side of the circuit to the other one. We usually call these circuits the data path. Why? Because data propagates along here and gets manipulated along the path. Now, while it is getting manipulated, if it always does exactly the same operation, that's also okay. But in a lot of cases, there is something that is different, and we are not always doing exactly the same thing. For example, sometimes we are doing an addition, sometimes we are doing a subtraction. Sometimes we are taking this output. You know, let's make it even more fancy. Let's put another multiplexer here. And what shall we take? How about this one? Completely random. Don't try this at home. Don't improvise on the blackboard in front of 150 people and 200 people watching in July. Not a good idea. Okay, so that was the data path, and there's a couple of decisions to be made. Do I do an addition or a subtraction? Do I select the upper one, which is the result of the addition subtraction, or do I take the multiplication? Do I take this AND gate and bring it, or do I take whatever was selected behind? Those are decisions that we are making, and those decisions are made and can change at every step that we are doing an operation. It might be that first I do an addition and directly have it out. In the next step, I take them and I multiply them, and then in the third step, I do an AND of these operations. Why not? I could do that. I have the flexibility to do it. So there is a part which usually then goes this way, I mean, when we are drawing it, that we call the control. And we say that there is something controlling our data path, decides what it will do at every given step. And during this step, I have a finite state of possible things that I could do. It's not like infinite, right? I could either add or subtract. I could either take this or this. I could either take this or this. So I have three decisions. At most, I could have how many different states? 3, 4, 5. That's 8. Somebody said 8. Anybody objecting? We are in a democratic country. Who says 8? Maybe it's 7. Okay. Not everybody is convinced it's 8. We have a number of states, a finite number of states, and we have a control block that can move you. Once you know we are in one state, we can decide to move to the other state based on this, or maybe based also on some inputs. We can say, hey, I first do this, then I do this, then I do this. Now, the combination, both of them will end up being sequential circuits, because at the inputs, we are going to have some state holding elements. At the output, we are going to have some state holding elements. And inside this control, we are going to have some state holding elements. Technically, both of those will be sequential circuits. However, the way they behave are slightly different. Here we are manipulating data. It's a very regular data flow. Whereas here, I move between, it's usually for a control purpose. I'm here now. I know what I have, and then I will move to the next state, and I will move to the next state kind of thing. So the distinction is not super clear. You are wondering what I will ask in the exam. I know, don't worry. But knowing the difference between the two, what we are designing, will help you construct your code in Verilog once we describe them much more easily. This is why I'm spending so much time on it. Now, we talk about RTL design, and RTL stands for Register Transfer Level. And registers are the state holding elements when it's not 1 bit, but 32, 64, 256 together. And it means that we are describing what happens when we move from one register to the other register. We say the description is defining what happens between consecutive state holding elements, what happens in between. That's why we call the design flow usually RTL design. So state is stored in registers. There are distinct time slots, all of them the same length. Every time slot, inputs and present state is used to calculate the next state. And once the time comes, the next state is stored as the present state, and the cycle starts again. In a typical laptop, computer, cell phone, this is done 1 billion times a second. 1,000 times, 1,000 times, 1,000 times. Now, RTL definitions can be used for data path circuits. These are the ones that I was showing where data more or less flows and gets manipulated. And here are my favorite multiplexers choosing which one of the possible outputs I choose. Or finite state machines, which are predominantly used to generate control signals that actually tell you which part of the circuit, which part of the data path to take. As I said, knowing the distinction is not so important, maybe, but it helps you designing circuits much, much more easy. Now, it is hopefully clear at this moment that the most interesting thing we have to learn is, how can I store the state? We will talk about circuits that we say are bistable. They have 2 stable states. They can store a 0, they can store a 1. And we will see, I will ignore this. In the book, you can read about it. I'll start with the D latch, and then we go to the D flip-flop. Are we excited? Yes, we are. So let's start. We are totally not excited. Okay. Now, the simplest bistable circuit and the heart of most memory elements is a structure like this. So, sorry, I have to, again, I'm bad at this. Okay. So, it's the same as the slides, by the way. I mean, I'm just drawing it slowly. Give me a number, 1 or 0? 1. Okay, so this is an inverter. If it's 1 here, this one will be 0. And since the input of this inverter is 0, the output of this inverter will be 1. And if we want to make a feedback, close the loop like this guy is actually stable. My input is 1, my output is 0, my output is 1. That is the input of this guy. So they agree. This is like 2 friends talking to each other, positively reinforcing each other. Yeah, that lecture today was horrible. Yeah, it was horrible. It was horrible, right? I hated it. I hated it even more. So the thing stays. There is nothing moving it away. However, you will realize that whether or not I have a 1 or 0 is arbitrary. I could just as well change it, and I could start with a different color, 0. Well, if I have a 0, this guy will be 1, this will be 0, and 0 will go back again and reinforce itself. The same thing. So we have a circuit that could have stored either a 1 or, depends on which part you say is storing it. You could say this part is storing it, this part is storing it, this part is storing it. It's not so important. The important thing is that this circuit has 2 stable states which we can call and which we can remember. And the important thing is, it's the loop that keeps the thing stable. Isn't that great? So this is one, and this is the other one. Looks like the best thing in the world, but how do I go from one state to the other, right? I mean, it's obvious that magically I can come to this state and I will stay here, but I mean, what good does it do? How can I manipulate it? How can I make any use of it? Now, this is where things get interesting. Again, sorry about the turning on and off, but it is apparently needed for the recording. Now, I do two things. I add a switch here, and this loop, I also add a switch. Now I have a controllable element, and I can have an input. I'm just going to call the input D, like data. And I have an output that I call Q. No idea. And somehow this thing is going to work. Let's first get rid of the data, what is happening here. And I will realize that I have two different functions that I can perform here. The first one is, if I want to keep the value, I need the loop. So to be able to keep the loop, which is here, I will just close this one while I keep this switch open. So if I close this guy, don't worry, the slides are there. You know, I'm just drawing it once again. This is a circuit we already had. So whatever value is here will stay. It will stay until I do something else. When I want to bring a new value, I could do the following. I say, you know, loop, go away. I open the loop, and I close the input. And now, whatever the input is, will come here, will get inverted once again, and I have the input connected all the way to the output, which is good. When I want to keep this input, I'm going to, at the same time, very carefully, two people, right? One of them will close this, the other guy will open that. So I close this, ba-bam, and I open this, ta-da. And now, if I change this to something else, still this guy is, whatever the value was, stayed in there. I memorized my input. Okay, showing it on the blackboard was bad. So let's see how it works. Once again. So I have two distinct states. We add one switch to the input, we add one switch to the loop, and we make sure that when one of them is closed, the other one is open, and vice versa. So to do that, I use my, well, I can give some names to these things. So I named the input D. I didn't draw it there, but those secretive switches were moved by this signal that I called clock. And if I have clock through here, I have the inverted version going here. And then I called that output Q. And now there is the same thing I tried to do there. So I have two modes. In the latch mode, the loop is active. So here is Q, here's Q bar, here's Q. I'm remembering it. This input can change as he wants. He can say, I'm 0, I'm 1, I'm 3, I'm 7, whatever. The loop will just ignore it. It's closed. It's not connected to the input. Until the point where I want to memorize it, then I will say, hey, I will switch the latch to what I call the transparent mode. Now the input will be connected all the way to the output. And to remove any bad influences, I'll just open the loop so that nothing is against this value. Nobody is fighting against it. How does this sound? It's okay? Yeah, question. Yeah, bad, right? Because in a fight, and this is true for everyone who's been in a fight. Okay, physical? Yeah, okay. When you go in a fight, there are no guarantees, you know? You don't know what the outcome will be. You will have to accept the fact that you are going to get punched in the face, okay? So generally, I don't know what the other colleagues who have been in a fight will tell you, but if you're not prepared for it, don't go in a fight. It's not very good for us. It's not very good for our design. We try to avoid making these things happen so that we don't have conflicts. However, next week, we will talk about setup time and hold time. Remember that discussion. That discussion is actually exactly what you tell about, that we try to avoid conflicts in a way to give it enough time so that they can go from one mode to the other mode without conflicts. So what we will do, and this is actually a very good question, we will ensure that the time that he is memorizing things, we give it a little bit of time, a truce, you know, say, you know what, do whatever you want, change, carry back and forth, but just before this guy memorizes, and a little bit after that, please stay silent, okay? Very good question. Others? Yes?
Why don't we add the switch directly after the second speed? And now we would still have the over when not wanting to use this memorization. We still have the overhead with propagation time of those two inverters.
Yeah, it's a valid question. However, if you think about it, or we can discuss about it longer, you will see that we need two switches. We need to open the loop and we need to open this thing. Where we put it technically doesn't matter so much. And that propagation will happen one way or the other. So whether or not it happens before the loop or after the loop will not matter as much. That time, physically, because, you know, light speed plus these guys reacting will have to be there. Whether or not it counts to the memorizing process or it counts to the propagation delay is a bit of an academic discussion. We can take that offline. Can we take that offline? Thank you. Sorry, I'm not trying to walk out of it, but that one will go for a while. Okay. Other questions? I might even answer some of them. Come on. He's really upset. Yes.
You have to close both switches at the same time. Like, can we replace that switch with a resistor, for example?
I mean, we could do a lot of things. It's just not needed.
Yeah, but like in my mind, it's a better example. So I'm not.
Oh, okay, we are not going into the details of how the switch is constructed. Technically, it will be two transistors, a PMOS and NMOS working in parallel, but it's because this is not the type of course where we talk about the details of how the switch is implemented and what kind of techniques can be used to improve its performance. We are not really going into that. Is that okay? I don't want to have my record as ignore twice the question. Yes. Why do I need? Well, first of all, I mean, very, very fair question. First of all, the NOT gate is the easiest gate we can make. It's just two transistors. There is nothing easier we could make. So if I'm making any active circuit, meaning any circuit that amplifies the input signal and restores it again at the output, this is the simplest, smallest thing I can do. Now, I want to create a loop that is stable, that doesn't fight against itself. So if I had one doing this, the guy would go crazy. No, I'm one, I'm zero, I'm one, I'm zero, you know? So I realize this is the smallest one. I add another one so that we agree on the value, and then I close the loop. See, I can answer some questions. Yes? Yeah, I mean, you can say that this thing is a buffer, like this. And you say, I have just one buffer in between. There was one thing.
How can we keep the current flowing in this loop without creating a perpetual motion?
It's not a perpetual motion machine because these gates have their own supplies. So this one is connected internally. We remember there was this one lecture where we were talking about, I said, hey, this is the only time we talk about, but there will be transistors that are connected to a power supply. So they draw current from there, so actively. So they consume power actually keeping it. It's not like data freely circulates like that. It's actively being kept this way. And if you turn off the power, this thing will lose the content of the memory. One? No? Ah.
I don't know if this is a relevant question, but I mean, I understand how hard drives work. You just write some stuff onto this, but the solid state drive, as I understand it, kind of traps electrons or some magical thing. How does that work? Does it have any relation to that?
No, not really, but we will. It's a good question. The answer will come like in about 5-6 weeks. When we come to, we will first see processors, and then we will go into memory systems, and then we will talk about the different types of memories we have. And then we will move from, this is what we call CMOS logic, SRAMs, registers, SRAMs, DRAMs, and then we will come to hard disks and non-volatile memories, how they store. The principle is the same. Somehow you have to keep a 1 or a 0. Whether or not you keep it as a magnetic, a change in the magnetic direction, a charge on a capacitor, electrons in a field, spins and resistive value changes, whatever, that will not be so much of our issue. But there are multiple technologies to do it this way. What we will then talk about is how fast can we do it, how fast can we memorize it, how dense can we make it, how much do we pay for it. More? Yes?
Why can't you do it in but like, why can't you just have the begin for example, and switch?
Why don't I do it here? Yeah, excellent question. Why do I have these gates? Because these gates are active. They, whatever D is, not D is actively being driven by a circuit. So he takes power, he drives it, actually he drives down for D minus, then he drives it up again, so restores the signal. That is a quality we want.
Otherwise, you just have like the signal will just die down.
Well, the signal we will try to capture it somehow, but we won't really manage because these guys are also electrical pieces. And guess what? They are not ideal. So they will leak currents, there will be transistors there doing all kinds of things. We want to, have a strong presence saying, I'm 1, I'm 0, I'm 1. Okay, I agreed, let's stay there. Excellent questions. I'm moving one slide. Okay, so I hope you don't, I mean, we are not going into the transistor level design, but I hope I have convinced you a little bit that we have a simple bistable circuit. We have 2 modes. In one mode, we are transparent. The input propagates to the output. In the second mode, the latch mode, so in one mode, the input here propagates all the way to the output. In the second mode, the data stays here in this loop and is at the same time available to the output as it was stored before. So this was the one property that we wanted to do. And who is controlling these switches? Well, these switches are being controlled by this magic clock signal that we were talking about. That we can have many of these at the same time and regulate it and work with it. Now, we have a great circuit, right? How do you feel about this guy? It's good, it's simple, it's really simple. It's one of the smallest circuits. There is, however, some small flaws. You will not like working with it so much because it is transparent when the clock is 1. So there is like this entire straight through path which goes directly to the output. And people have realized that it might be simpler if instead of this guy having one state where it memorizes and one state where it is completely like a wire, let's have something that can memorize at an instant, not during the entire time the clock is 1, but at the time where clock rises to 1 or just falls. Whenever there is a change in the clock signal, so if my clock goes like this, like 0, 0, 0, and then he rises, in a latch, you could say that during this time, the input will be connected to the output, and here I will keep the data stored. What if I could just memorize at this instant, this very short time? It's like a, you know, snapshot with a camera, right? Like you're seeing, eyes closed, eyes closed, eyes closed. I open, memorize, and close my eyes. What if I could do that? Wouldn't it be great? And a lot of digital circuits students say that would be awesome. And that's why they did this. So this is why we call a rising edge triggered D-type flip-flop. Couldn't be shorter. Now, first of all, it's called an edge triggered device because it is activated on the edge of the clock signal, not while clock is high and while clock is low. This has the advantage that I know exactly the instant where something is happening, here. And then the next time, you know, I do my job, and I do my job, la, 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 la. And then here is the next time the clock rises again. At that time, it samples. Why is it called rising edge? Well, clock has 2 edges, right? If you want to rise a second time, you know, and this is your active edge, at some point you have to fall. Makes sense? No? Okay. And we could have chosen either one. We just have to be sure to agree among all the flip-flops in this circuit that we do it at the same time. Otherwise, life gets a little bit more complicated. So we say rising edge. If the thing happens here, we would have said falling edge if it would happen, if the memorizing process takes part here. Is there any advantage over the other? Absolutely no. Why do we use rising edge? We are positive people, okay? We like a rising story. We don't want falling edge. Rising edge, okay? Makes no big difference. So how does it work? When clock rises from 0 to 1, the input passes through to Q. That's simple. I'm a rising edge triggered D-type flip-flop. I don't care what happens. The clock changes from 0 to 1. I open my eyes. I memorize it. 5 people here. I close my eyes. 5 people, 5 people, 5 people. I keep this value. Whatever I saw there, whatever the value was at the input, I keep it. Just that small instant where the clock is transitioning from 0 to 1. Well, how much is an instant? Well, the 10, 20, 40 picoseconds, whatever. I need some time to memorize it, but not like half the clock period. Sort of. This side also, even in the back? No? Okay. Some people say it's okay-ish. Now, if you are really, really curious, the way this is done is by putting 2 latches that have alternate clocks. Is it really important that you have to know this? Well, you should know that a flip-flop is 2 times as complex as a latch, okay? And a flip-flop can be constructed by combining 2 latches. This is what you should remember. The exact details is not so important, but what happens is when clock is 0, this one is transparent, this one is still storing the last thing. So the data propagates all the way to this N1. And it stays there because this guy is still keeping the other one. Data is here, it's changing back and forth. And when clock then turns from 0 to 1, This time, this guy stops letting everything through, and this guy lets things through. So from the outside, what you see is that, hey, D is changing here as they want, and Q only changes at the moment he transitions from 0 to 1. Okay, if you say so. So what are the changes and differences? Oh my God, no, I should have done this in 2 steps. Okay, so this one is the latch. This one is the flip-flop. How do I tell them apart? Well, nobody agrees on them. Even some books have it in a different way. But generally, when you draw these things and you put like a squarish box for the clock connection, you say this is a latch. When you put a triangle like this, you say, ah, it's a flip-flop. This one triggers at the edge, and this one triggers when the clock is high, meaning the entire time. Now, we will not be using circuits where we are mixing them. And since we like, or it's easier to talk and work with flip-flops, for the rest of the lecture, we will just be looking at flip-flops. Okay? Trust me, it's easier, it's nicer. Of course, don't trust what I tell you, but you know, maybe be curious about it. Okay, so how do they work? What's the difference? This is the clock signal. The clock is going to both of them. This is the input that is going to both of them. Notice that he's changing here in the middle, then he stays, then he changes here in the middle, then he changes, dips once again. Now, for the latch, we have 2 modes of operation. In this one, while the latch, when it is 1, meaning that during this time here and during this entire time, the latch is what we call transparent. Whatever is in the input will propagate to the output. Not exactly at the same time. What is this? What's this difference in the time? Yeah? The propagation time that we were talking last time. It doesn't happen instantaneously. There's a bit of time. If you remember in the latch, there were these 2 inverters. Somebody didn't like it. It has to propagate through and come out. So there is a bit of a delay. Maybe even a bit more delay, not only what I showed, maybe there's something more secretive. And then the data stays like this. Now we are in the memorizing state. Okay, nothing happens. And then here, I'm changing the input and the output changes directly after with some propagation delay time. And now I continue, the input changes again, but this time I'm not in the transparent mode. I'm in the part where the latch has already memorized. So the D has been disconnected. We are in the loop. So at this point, even if the input is changing, the output of the latch is not changing. Now, realize that sometimes the output changes, sometimes it doesn't. And it depends on whether or not the latch is transparent or the latch is in the latch mode, in the memorized mode. Flip-flops, on the other hand, this is my argument. This is my argument before we go to the break. Flip-flops are great because you don't have to think too much about them. The only thing that happens is at the rising edge. Here is the rising edge. Data is what? 1. Good, I store 1. I don't care what happens here until the clock rises again. The clock rises here, what's the value? 1. Okay, the output is 1. How simple is that? How great is that? Look how much I was struggling with the latch and how faster I was able to explain. No? Okay, maybe give me the break, and after the break, maybe I'll be much better, who knows? Sorry, your question first. They told me that my explanations were so bad that there were many requests to the website, and the website crashed. So IT is trying to fix the DDCA website. Okay, go easy on it. No? Okay. Let's see if we can make sense of this lecture. So number of things will become clearer because we will be discussing these things over and over again. Especially this diagram looks a little bit scary. There was one question, how does this D relate to this clock? I'll come to that, okay? At the moment, the only thing we were actually trying to see is how does the difference, what's the difference between the output when we have a flop? What's the difference when we have a latch? And the thing that we wanted to sell you, you know, this is the marketing part, is that, okay, we told you how latches work. They are good, they are nice, but we will be using D flip-flops because they are so easy, so nice, so cool, so cute. Okay? Seems like a reasonable explanation to me. Okay, now, let's stay under this assumption and let's just try to move ahead a little bit because this lecture I want to talk a little bit more about what we can do with these flip-flops. So one flip-flop is 1 bit. One lousy, tiny bit. You cannot even enter your grades with that. So for that, you would want to have multiple flip-flops so I can combine multiple bits together. I have states that do more than just store 1 bit. The moment we have multiple bits, we usually end up calling them registers. And it's a very loose term, register. Basically, it's a collection of flip-flops. Can it be latches? Sure, why not, if you are really hell-bent on using latches. So you would then draw it with something like this, where you say, I have a 4-bit D signal, and I have a 4-bit Q signal. Needless to say, there are 4 independent parallel flip-flops. Their inputs and outputs are D0 to Q0, D1 to Q1, etc., etc. That looked easy. Now, there are cases where you say, I don't want that the flip-flop works every single clock cycle. Not at every rising edge should it memorize its output. There should be some times where the flip-flop just ignores things. And for that, we have what we call an enable flip-flop. Interestingly enough, and I have very good reasons for that, practical reasons, we don't want to manipulate the clock. We want clock to be a pure nice signal that is not being manipulated through combinational logic. So instead of not sending him the clock signal, we do the following. We say, hey, Frank likes multiplexers, let's put 1 here. The D will go through if there is an enable, otherwise I'll just give back what the output was and memorize it. Looks like a waste of time. It is a safer and nicer way of doing things. We call flip-flops that have this capability flip-flop with an enable input or an enable D-type rising edge triggered flip-flop. Okay. If you like this one, you are going to fall in love with this guy. Resettable flip-flops. Now, one of the mysteries of the world is when you switch on the power and you have a bunch of flip-flops, what will they memorize? Will they be 0? Will they be 1? In fact, it can be shown that under some circumstances or most circumstances, their internal state will be random. People even use them for random variables or fingerprinting purposes, meaning that the flip-flops of every manufactured chip will behave differently to each another, like a fingerprint. And they use this to detect whether or not things are being done. Anyway, I'm losing track again. Resettable flip-flops have an additional input where you can use a signal to set the value of the flip-flop to whatever you want it to be. If reset is 1, the output is forced to 0. If reset is 0, the flip-flop behaves like an ordinary D flip-flop. Now, there are variations of the theme. there are the ones which have an active high reset, meaning that if reset is 1, is resetting. There are ones which are active low reset. A reset is made when signals are low. Yes? Excellent question. We have both types, and we will differentiate between them tomorrow. I think tomorrow I have more to say about that, but we have both types. Yeah, sorry, directly this slide. Synchronous resets at the clock edge only. Asynchronous reset means that I do it immediately. I don't care what happens at the clock. Synchronous says, okay, everything happens at clock, so when the clock comes, I'm going to do these things. Now, yeah, if you have resettable, you also have settable flip-flops. The idea is the same. You may want to have the initial value of the flip-flop to be 1. So the signal in this case is called set signal, not reset signal. So reset signal would set the output to 0. Set signal would set the output to be 1. Now, these are just the basic building blocks, but what we want to do is do interesting things. Now, for the data path, which I'm drawn here, all you need is actually to put these banks of registers into the data path to wherever you want them. Nothing much to talk about. The interesting part are these finite state machines. And so we will be discussing for the rest of the lecture with the finite state machines. That was a good intro music, come on. So finite state machines can be really, really, really easy, or it can make your life hell. So tricks for making things easy is the following. You have to realize that every finite state machine has 3 parts. So I will write them down here. So the first part is the state register. This is the one. This is essentially a bunch of flip-flops that when the clock comes, switches from next state, switches the current state to the next state. That's all it does, a bunch of registers. Now we have a next state logic, which is, I'll just write it here because we should keep this, next state Well, the next state logic is a combinational circuit. It calculates what the next state is going to be. How is it going to calculate? He's going to look at the inputs, and he's going to look at the present state, the current state, and out of these two, we'll say, if my current state is this, and the inputs are there, probably the next state is going to be this. Haha, here you have it. And then we have the third part, which is the output logic. Because if our circuit is doing something and nobody hears about it, is it really doing something? You know, you need an output so that this circuit matters. For example, the output logic will be driving these signals of these multiplexers or external control signals to say, hey, I'm in this state, explode the bomb, initiate takeoff, something like that. Yes? Well, the output logic will drive the outputs, and the outputs are, you know, things that are connected to your circuit. The next state logic is going to determine what state you are in. It's the internal state being moved to another thing. Yes. Are we excited about these finite state machines? Yeah, okay. Finite state machines get their name because a circuit with k registers can only have 2 to the k states. AKA, the number of states that such a machine can have is finite. And there are 2 types of finite state machines. Actually, there are 3 types, but we are just focusing on 2. And the most annoying thing about these finite state machines, and later on we will talk about caches, the same thing will happen. There are millions of names they could have given, but the two ones have very similar sounding names. One of them is the Moore state machine, the other one is the Mealy finite state machine. There's a third one, it's not so important. Guess what letter it starts with? Medvedev, yes. So 3 state machines, all of them start with M, crazy. So what's the difference between them? We have our 3 things. We have the next state logic, the state register, and the output logic. The only difference between them is the output logic. If the output is only calculated through the present state, we will call it a Moore finite state machine. If the output is calculated from the state, as well as the present inputs, we will call it a Mealy state machine. And I have a slide at the end. There is a bit of a tradition with me. I always 100% ask a question about, is this Moore Mealy or something Moore Mealy in the exam? 100% every time. Okay? You're welcome. Who believes that I hold my word? I will ask one. And I'm sorry to say not all of you will answer it correctly. I'm sorry. It's just, I totally trust you. It's just long year statistics. There was a question, sorry. Sorry? Can I draw a circuit with flip-flop? Yeah, we will do one. In half an hour, we should be done. If not, tomorrow we will definitely get it done. It is coming. It is coming. Now, one little word of warning. It is known that I'm not a super big fan of the examples in the book, but I use them in the lecture nevertheless. The main reason is that it makes it easier for you to study because the slides and the text in the book that explains those figures correspond to each other. And I think this is more important than me liking the exercise. But a very classical example for finite state machines are these semaphores, these traffic lights. So in this case, we have 2 roads, this one, Academic Avenue, and the Bravado Boulevard. So creative. And we have 2 sets of lights. So lamp A on this side of the road and lamp B on this side of the road. And we have a bunch of sensors that sort of send an input signal. So if cars come here, it knows that there are some cars, so TA is 1. And if there are no cars here, there is no traffic there, so it's 0. Are you comfortable with this exercise? We are now going to design a finite state machine that sort of regulates how these lights turn on and off. And the minimum number of people are killed due to traffic accidents. Okay, so, whoa, wrong side. So what we want to do is build this traffic light controller, which will be a finite state machine. Its inputs are those 2 sensors, if you want, whether or not there is traffic on road A or traffic on road B. If there are cars here, this will be 1. If there are cars here, it will be 1. No car 0, no car 0. So this will be the input. Internally, I have a state, and this is not combinational. I will not be able to determine what the state of the lights are just by the current thing, because, you know, if the light is green, I first have to switch the other light to orange, then the other light to red, make sure, then switch the first light to orange. You know, there's like a progression of things happening. It doesn't happen instantaneously. This is why I need those states in between. And I have as an output the lamp control. So there is the lamp for A and the lamp for B. I have 3 lamps, red, orange, green. So I need at least 2 bits, right, to express those lights. And so those are my outputs. I have a reset because every morning or after a power breakdown, somebody has to make sure that these lights start at like a known interval. Like first, let's give the A side the road, then the B side the road, etc. Okay. Okay, let's see. So, for reasons that we are not discussing yet, we have decided to use a Moore FSM. In this case, the output will only be determined by the state, which is very good because I can draw a state diagram and I say when there is reset, let's start in the state that I very creatively called S0. And since the moment I'm in a state, the output will only be determined by the state, I can just write the outputs inside the state. Because whenever I'm in S0, lamp A will be green and lamp B will be red. That's my default. It could have been anything else, but because I'm the architect and I have an affinity, let's say for the academic avenue, I decided that in the morning when I press the button, let's first go the academic avenue. Now I can continue doing this thing and I say, what will happen? Well, as long as there is traffic, let's stay here. If there is no traffic, let's move to state 1. In state 1, B is still red, but let us turn the light, this light to orange. And then let's not wait at all, move to the next state. And in this state now, A is red, and we switch immediately without any yellow, we switch directly to green. And we stay there as long as there is traffic on B. And if there is no traffic, now B turns yellow, A is still red, and then we move to the phase where B is red, A is green, and this can go on forever. I have 4 states. It has a finite number of states, 1, 2, 3, 4, right? And that's a finite state machine. We solved the traffic problem of this utopian city. Who drives cars here? Whoa, okay. Do you think that's a great idea? That as long as there is traffic coming, that the light will stay green, as long as it's on your road, right? Okay. We are not making our life complicated, right? We could have had other issues, we could have had timeouts and things. We're just keeping things simple. Okay. Now that we know, given a state, given the input, what will happen next, I can actually draw a state transition table from this diagram. It's important to have this diagram. It's important to know what we are doing. But once I have this, I can quickly transition into this. And I can say, hey, if I'm in current state S0 and TA is 0, I don't care what TB is, the next state will be this. Let's fill the table, sorry. I don't care what happens, as long as TA is 0, I will move to S1. If I am in S0, as long as TA is 1, I stay at S0. That was the part where the light to this thing is going on. Now, here is one problem. David and Sarah, if you're listening, I'm very sorry. Here is one problem I have with it. Calling them S0, S1, S2, S3 is really annoying as states. It would have been so much better if they had like meaningful names, like, A is green, B is green, both are red, or something like that. Anyway, we can complete it, and it's not that crazy. If you're in S2, doesn't matter what TA is. If you are at 0, you go here. Or if you're at S3, I don't care what the inputs are. I will immediately go to S0. That sounds okay? Now, once you have that, you can start saying that, I had these states. I had 4 states. If it is 4 states, I can pick an encoding. Now, this encoding is arbitrary. I could have chosen any encoding I wanted. This is one of the many possible permutations, but I said, let's make S0, 0, 0, S1, 0, 1, S2, 1, 0, S3, 1, 1. Boring as hell, why not? Okay, And now I can replace wherever I had my state with the corresponding encoding. All of a sudden, this looks more like a truth table that we were looking at the combinational circuits. And now I can also write the next states, which are outputs of a combinational circuit. Look, I have 4 inputs and 2 outputs. This is one for which I can write sum of products, products of sums equations. And this is another one for which I can write that. And I promised that this would be interesting. Okay, so let's do it. Do you see how wonderful the exam questions could be? Write the next state equations. Okay, you look at S1, this one, and you can try to figure out what these things are. And using any method available to you, because it's a lot of things to type and write and draw circuits, we might even see some simplifications either through K-maps or by visual inspection. And we say, you know, this next state of S1 will be calculated like this. Good. I have a part of circuit. So what did I do? I calculated this part. So the next state was calculated out of the state holding a register, so the current state. Right? I took the current state. This is some combinational logic. And I had my inputs. In my case, the inputs were TA and TB, right? And where am I storing it? Well, we already know that this will be a flip-flop, D-type rising edge flip-flop controlled by the clock. And we might even have a reset. Let's write it here. There's a tiny reset here. Okay. The job of this thing is knowing what state we are in, knowing what the inputs are, trying to figure out what the next state will be. There, we can write a truth table. The truth table will reveal itself to be a combinational circuit, and we can do that. Now we have the output table. Now that I know what state I am in, I want to calculate my output. What are my outputs? I have 2 lamps. And I know that what happens in, I have 4 different states, and in each state, the output is given. In the first state, A is green, B is red, yellow, red, red, green, red, yellow. And now I have the same trick. I could have had any combination of bits and encodings. In this case, I said I'll use a binary encoding. 0, 0 is green, 0, 1 is yellow, red is 1, 0. And guess what? I'm going to fill this thing in. Well, now I have actually 4 outputs, which means 4 formulas, 4 Boolean equations, with only 2 inputs. Okay, let's put in the values, and let's write it, and then we will see that, LA1 is this, LA0 is this, LB1 is this, LB0 is this. What we did now is we generated the output logic, which took only the current state and produced the outputs LA and B. Every finite state machine is built out of these types. As long as you manage to keep these 3 parts separate, your life will be super easy. Unfortunately, what happens, not when you are drawing it, but when you are writing very low code, which we will discuss tomorrow, people tend to write everything inside each other. Instead of clearly separating, this part of the code does the next state logic, this part does the output logic, this part does the state register. They tend to bunch everything together. That's when mistakes happen and life gets complicated. It still works, it's just more difficult. Questions so far? Somebody said we should be drawing them. So let's start drawing them. So the first part is our state register. I have my current state is this part. So we are drawing this thing here. That's my flip-flop. In this case, I drew only one. I understood that this is 2 bits. In this case, they made it look like, okay, two separate inputs and outputs. It's a small circuit, so we can afford to do that. Okay? Then the next state logic. Well, my circuit is still here. This is my next state logic. So we are doing this part here. And I have my two inputs. I did the Boolean logic minimization kind of thing. Remember, I had my things. And out of this, this was the equation for S bar 0, and the other one was for next state 1. So the bit 1 of it, bit 0 of it. Okay. And now, very, very surprisingly, I'm doing this part. From the current state, I calculate this output. And every output has a different logic. In this case, they are very, very simple. And I get my output. Now, there's a lot of arbitrary decisions that were taken here. And they would have affected the results if you're doing this on your own. The first decision that we have taken is the how I call these states. You know, is this state 0, is this state 1, or whatever. The next thing also related is how I encode them. Nobody says that S0 should have been 0, 0. It could have been 1, 1. The next one could have been 1, 0. The next one could have been 0, 1. As long as they are distinct, I'm good. Nobody even says they have to be 2 bits. Okay? Do you agree to that? They have to be at least 2 bits, but they could have also been 4 bits, 3 bits. You could have also made 17 bits, but in that case, most of those bits would be useless. There's only 4 different states, right? The next thing that was arbitrary was how I did this encoding, or how many bits I used for the lamps. That was also arbitrary. Depending on that, the equations that I come up with would be different here and here. They all depend on what was the state encoding and what was the output encoding. I could have manipulated it so that I get a simpler circuit and things like that. Fortunately for us, it will be only in the exam that you will have to maybe solve a question like this using Carnot maps, equations, and things like that. For most other cases, we'll be using Verilog to describe the combinational circuit. We will write a few lines saying, hey, if this, then next state should be this. If the input is A, and our current state is this, next state should be this. We will be describing this in a behavioral way. We were talking about that before, and our life will be easier. Now, what will happen? Well, we can now go through, and since we have this circuit, we can simulate it. We have multiple cycles, and in each cycle, one of these things is going to happen. We start with a reset so that we come to a known state. We have drawn and we made it so that when there is reset, we land in the state S0. This is where we land. Before that, we don't know. Those things could have been anywhere. It's random, I told you, right? So there was hey, it could be something or something else. I don't care. That's why I use reset. Reset comes, these guys find their values. Now I'm in the next state. Traffic A is there, so I stay there. Traffic A, I stay. Now, magically, cars disappeared. No more, the avenue is gone. The avenue is empty. We realize this, and in this state, we say, okay, if there are no cars, let's maybe switch to the other one. What would happen if suddenly a car showed up here? That's a good one. I should ask this in the exam. Yeah?
I think it would go, it would go to A1, but we already send the signal, so it doesn't change the outcome.
Okay, he says what do you mean outcome doesn't change? Will it go to S1 or will it?
Go to S1.
Okay, he says it will go to S1. Very good answer. Anyone who says no? Not a single person?
I think it will stay the same because the cycle is not going to short. It's all about exactly when the cycle 4 ends, which state you're in at that exact moment.
So that is the important point, right? You memorize the next state when the clock comes. And the clock, in this case, is coming, where were we, TA? The clock is coming here. So I could momentarily have all the cars gone, and then a car could pop up here, and I would still stay here because the time for the decision is this point. If at this point, TA is 0, that's my sampling point. That's when I look at the result. That's when I move the state. The state can change its mind. Oh, I'm 1, I'm 0. Oh, cars, come, go, Lamborghini, and like whatever, bicycle, slowly, fell down, got up, no, he stayed. Oh my God, I don't care. This is the only moment. You can imagine that that light controller doesn't care. Cars are coming, going. I don't care, I don't care. Clock, car. I stay there, okay? It was very good input. Everybody on the same page. This is important because if you don't get this, everything else will fall apart. No? Itching, hair. Okay, online? I don't see anybody online. Okay. July, just rewind 35 seconds once again. This time, not double speed. Okay. Now we are in state 1. And once we are in state 1, we know that, I mean, from the diagram, there is nothing. I don't care about the inputs. I will immediately move to the state 2. And then I stay in state 2 as long as I have cars. The moment cars go, I say next state, and then I move. And once I know the state, I also know what the lamp of the avenue is. I know what the lamp of the Bravado Avenue is. Now here's green and red. We go to state 1, lights turn yellow. And then in the next state, Bravado turns green, and the other one turns red. Otherwise, we have accidents, and so on and so forth. We made it. It wasn't even that difficult. Okay, 12 minutes. I'll make this. I feel great. Okay, so as I said, the encoding could have been anything. In this case, we use the binary encoding. We could also use what we call a one-hot encoding. In one-hot encoding, what you do is every state has 1 bit. So if I have 4 states, I use 4 bits. And at any given time, you know, that bit is a 1. Makes sometimes, so for 4 states, this could be your one-hot encoding. It makes sometimes these calculations easier, sometimes not. It definitely requires more flip-flops because here my state is 4 bits. I could have used only 2, but now I'm using 4. There might be cases where I care. I'm a poor man. I don't have enough money to buy 4 flip-flops. And there are some times you say, hey, this is more elegant, I like it. Often the next state logic is simpler. Now let's come back to the Moore and Mealy FSM. Why are they different? For this, we have a great example. I really don't like this example, but okay. There is this cute snail, and the cute snail is walking over a, it's really silly. It's walking over this ticker tape, and it's 0, 1, 0, 1, 1, whatever, something written. And this snail smiles whenever the last 4 digits it has crawled over are 1101. So 1110, 1110, okay? We want to make this. I think the authors just wanted to have fun with me. So the difference between Moore and Mealy is that the Moore output only depends on the present state, whereas the Mealy depends both on the present state and the inputs at the same time. The tricky part is if the inputs change, even though the state is stable, the output could still change. Whereas here, the moment you are in the state, the output is stable, nothing changes until the next clock. The only way to change the output is to move it to a next state in which the output is different. Whereas when you are in a Mealy FSM, the output could change even though the state didn't change, and we could go back and forth. Now, for this particular very forced example, you can see that there will be a difference. And it looks like this. So the reset is here. And remember that we want to go to a state where we have seen 1, 1, 0, 1. So for the move, we go, okay, I'm in the state. Do I have a 1? Let's move to the next one. That means that I've seen 1. And then if I still see another 1, let's move to the second state. That means that I've seen 2 1s. Now I need a 0. If I see a 0, I go to state 3. I'm almost there. And then if I move to the next one and still see a 1, all 4 conditions have met. This is the only time I'm smiling. Now, notice that if I've seen 1 and went here, then I've seen 1, and I continue seeing 1, I'm still here because, you know, if I see 1, 1, 1, it doesn't mean that I have to go to the beginning. I just have to wait for the next 0 to come, and following that, I need to see another 1. Okay, but is that part okay, the upper one? Okay, let's move to the lower one. Now, this is Mealy. In Mealy, first of all, the very big difference, huge difference is, I can no longer write the state, the output inside the state. The state alone doesn't define the output. So what I do is, I write it on the edges that move the states. And I say, for the input 1, the output will be 0. For the input 0, the output will be 0. That's a very, very big difference. Notice that I'm asking these questions in the exam. A possible exam question is, I show you a state diagram and I ask you, is this a Mealy or Moore machine? Very simple trick. Check whether or not the outputs are written inside the state or they are written on the edges as this. This one is Mealy, this one is Moore. You get your points, you are welcome. Now, what do you notice? You notice that while I'm going, hey, this is 1, this is 1, this is 0, and then this is the same state that I reached here. If the input is now 1, before I go to a next state, I can already say that I'm smiling. I don't need to move to a new state to smile. I can say, hey, I had 1, 0, and 1, smile. I had 1, 1, 0, and 0, don't smile. We go back. Yes? Copy?
Yeah, we don't need to do it differently from Mealy.
We could also do that, yes. We could. Well, let's not ignore the input. The input would move me to the next state.
When I'm talking about the output logic, you can just ignore the input in the output logic.
Well, if I ignore the input in the output logic, I'm making a Moore-type state machine, and I end up with that one.
Yeah, but it still has the same circuit as the Mealy.
Well, the only Mealiness of it is that I can change the output. The same state could have a 1 output or a 0 output. That's the only Mealiness of it. If you take the Mealiness out of a Mealy machine, why do you have a Mealy machine? Yeah. All right. I mean, philosophically, yes, I agree with you. But, you know, if you are not changing, I mean, if you can make a Mealy machine where the output is always the same regardless of the inputs. And you can say, I made a Mealy machine, but nobody knows about it, okay? Other people looking at it will think that you have a Moore machine. And you'll say, I tricked you. This was a Mealy machine that's hiding its identity. Okay, so now let's go and take, I'm not going to do this, but it's the same type of thing. You have 3 states now, and you have your input, and you can calculate your next states. In this case, notice that I had a lot of more freedom to choose the states. I only have 5 states, but I use at least 3 bits. So this means that there are three, how shall I say, parasitic states there. Who knows what happens when state is 111 or 110? Those are all possible things. They can be expressed, but they are not valid. I can fill my things. I can have my output table. In this case, my output seems to be a very simple function, y equals to S2. Why not? And I can do the same with the Mealy one. In the Mealy one, I'm not only calculating the next state, I'm also calculating the output. Now, superficially looking at it, you say, hey, one of them has a bunch of boring zeros and ones, and the other one has a bunch of boring zeros and ones. And I completely agree with you. I'll try to explain it. And then you can, do your calculations and come to your states, or you can have your Mealy schematic. They are different truth tables, so it also stands to reason that they have these things. Notice that you can still see this next state logic, state holding element, output calculation. Very important to keep them separate. Now, I lost the time. Yeah, okay. So this is what would happen in a Moore machine. So this is my input. It's coming. 1, I move to state 1. My input is 1, I move to state 2. It is 0, I move to state 3. It is 1, I move to state 4. And at this point, I'm smiling because I have already seen, I didn't see this 1, 1. I stayed here 2 times, but 1, 1, 0, 1. Next state, smile. And then go back and 1, 1, 0, 1. Next state, smile. Yeah, okay. The Mealy machine is a little bit strange because it's the same input. We are looking at the same input. 1, 1, okay. Now I moved one state. I moved one state. It is 0. I move to this state, and I am smiling already. I don't need to go to the next state to smile because I see that the input at this case is 1, and this immediately tells me that I already saw it. I can start smiling now. Notice that this guy needed one more state to smile, whereas this guy smiled 1 clock earlier. Its behavior is a little bit different. Okay, so this is what we read in the book. Now, here is the thing. Why do we care if it's Mealy or Moore? Now, the first answer that you have is because Frank will ask a question. I'm telling you I will ask a question. Definitely. But there is actually a very important reason why we care about Mealy and Moore. There is a very, very reasonable reason why we care about it. If you remember the combinational circuits, you are not supposed to have loops. Remember that? What's a combinational circuit? No loops. Now, if you have 2 finite state machines that are interconnected, if one of them is Moore, there will never be a combinational loop. But if both of them are Mealy, there is a chance that you can have a combinational loop. It doesn't mean that it will be, it says it can be. So the reason is if you have one finite state machine here, he has ready out, completed in, and you have another one here which says new data and data received, and they are sort of connected to each other, which is a signal data ready. This guy says ready, this guy says understands new data, and he says, okay, I have the new data, and he says, okay, I have completed. Now, if both of them are Mealy, that means that based on this data ready input, he could create the data received output. If this guy then reacts and takes this thing out, there might be a loop where these guys are like ridiculously fast, changing back and forth. This is why we want to make sure, or we want to understand what the outputs are if they come out of a Moore state machine or Mealy. As long as one of them is Moore, you don't have to worry, it will work. So tomorrow we finish the few slides here and we try to see how we can convert this into using Verilog. That's it.